This particular resonance tube is going to be activated with a signal generator, which is just simply a variable frequency AC power supply, and it's going to operate a loudspeaker, and you can change the frequencies of the sound coming down. You will get a standing wave setup because you've got a set of waves coming down like so. This end is closed, therefore you get reflections occurring. So you get a set of waves coming down, a set of waves coming back. They will interfere with each other. Superpositioning will occur, and you get the possibility of a standing wave setup. Now, it's called a resonance tube, and technically resonance is dealt with properly in the next module, not in this particular module. However, they're going to ask you in a moment, what is resonance? Why is this called a resonance tube? And what we're going to say is that the air in this tube has what they call a natural frequency. It's a frequency, I suppose you could argue, that the air wants to vibrate at. And you can tell when it's vibrating at this natural frequency because you tend to get nice big vibrations and therefore loud sounds. Usually when resonance is introduced, a pendulum is used as an example. A pendulum, if you set it in motion, will go back and forth at a particular frequency. There's even a formula which tells you how big the natural frequency is. This is the formula for the periodic time. It's 2 pi root times the L, which is the length of the pendulum, divided by the gravitational field strength of the Earth. The frequency, of course, is 1 over that. So everything has what they call a natural frequency. And if you can get an applied frequency, so say, for example, you came along and started giving the pendulum bob a nudge every now and again. It's a bit like getting a child on a swing to go back and forth with big amplitude oscillations. If you can match the frequency of the push that you apply to the natural frequency of the pendulum, you will get it to swing bigger and bigger and bigger amplitude oscillations. So it's to do with an applied frequency, like you pushing a child on a swing, and that has got to match the natural frequency of the oscillating system. So this loudspeaker is going to act as the applied frequency, and it is going to try and get the air to resonate. So if this frequency here matches the natural frequency of the air in the tube, you will get this phenomenon called resonance. And you know when you've got it because you'll hear a loud sound. Now, the resonance positions, or rather the resonant frequencies, there's not just one of them. The simplest standing wave is when you get a node at the closed end and an antinode at the open end. This is the standing wave that you draw. It's a quarter of a wavelength. However, you'll get a loud sound with that wave, no doubt. But if you increase the frequency of this, eventually you'll get another possible standing wave where an antinode is there, but you get a node there, an antinode, and a node here. And that also will give you a loud sound. So there are 2 positions, 3, 4, 5 positions where you will get loud sounds. And I've drawn the second one, the second resonance wave, as it were, in purple there. Anyway, part A simply says, resonance is the effect when you get exceptionally loud sounds being heard. Now, they're not that exceptional. But first of all, why does resonance occur? What they want you to say is that the loudspeaker frequency is equal to or matches the natural frequency of the air in the resonance tube. Now, part B then says that the method described will identify the first position of resonance. On figure 10.1, drawn the position of a node. You have to use a capital N and an antinode for the first position of resonance. Now, it's the green wave, and even though the wave is drawn like that, this is the mirror image of it, it does not mean that the air molecules are moving like that. We're dealing with a longitudinal wave. So if there is an antinode at the open end, is really there, then the molecules of air will be going up and down parallel to the direction of the wave, and it'll be going up and down with maximum amplitude. Whereas the air molecules just here, they can go up, but they can't go down because it's closed, and they tend to form a node. So we say that there's no vibration there at all. We simplify it a little bit. Then you describe basically what I've just said. Nodes, air molecules not vibrating at all. With the antinode, they're vibrating with maximum amplitude. Now, I wasn't sure what was on the mark scheme, so I also added vertically up and down, but that wasn't asked for in the mark scheme, because it does say, describe how they're behaving as they vibrate, and I didn't know whether they wanted you to say, is it vertically up and down or not, but they didn't. Now, the fundamental frequency is the frequency that causes that green wave to be produced. It'll be the lowest frequency, the fundamental, also known as the first harmonic. Well, you have to recognise that in actual fact what you've fitted into the tube is 1/4 of a wavelength, which means that the wavelength is 4 times the length of the tube. V is F lambda. You're told the frequency, and then you put the numbers in, and you get 342 meters per second, which sounds about right. Then the frequency goes up until the next position of resonance is produced. Now that's given by that purple wave. What's the frequency at which this will occur? Now you'll find it's 3 times the original, and I think if you just simply did that, you'd probably get the full marks if you got the answer right. But the reason why the frequency is 3 times the original is because you've now fitted into the tube 3/4 of a wavelength. Node to node is half, and you've got an extra quarter. So it's 1/4 of a wavelength, another quarter, and another quarter. So in this 75 centimeters, I've got 3/4 of a wavelength, and I've said that just there. That means that your wavelength now is 4L/3. And you put that new value for wavelength in, the speed of sound does not change. So you can have whatever resonant position you like, the speed of sound will still be 342. Now, the rather off-putting thing is that if you put your numbers in, you'll find that the frequency is also 342. And when I did that first, I thought there must be a mistake, because that's also the speed of sound, but it was just one of those things. That is 3 times that. Now, this is where it gets a little bit confusing. In other words, this second position of resonance is 3 times the original. That's called the first harmonic, so this is the third harmonic. The second harmonic doesn't exist. But because this is the first frequency, that can be superimposed on the fundamental, because you can put these waves on top of each other. That is also known as the first overtone. Now, they don't often ask you about that, but occasionally they have, and it can be a little bit confusing.